So just to get a sense of our class, how many of you are coming from outstation? How many of you are not in Bangalore in our cohort? Yeah, Suresh, I can see your hand. I can see
I
one.
think all put together less than 10 or so.
No. Okay, yeah. I can
I'm
see
also
some. Yeah.
from Chennai.
Okay. Yeah, it's sort of unfortunate today because, in-class sessions are always a lot more engaging in some ways as compared to staring at a laptop for 6 hours or 8 hours.
Actually, I was
True,
waiting
true.
for 3 years to be in on-class sessions. Otherwise, I would have taken this 2 years back.
I see.
Yeah, same here for me actually.
Oh, I see.
Yeah.
Interesting. Yeah, but unfortunately, so there was some uncertainty related to, today's Bandh, and we were just not sure whether, everybody would be able to make it or not. And I think it's sort of unfair, I think, to our participants that are outside the city. If the Bangaloreans in some ways get an advantage over the thing. And so we said, well, we're just going to move this completely online. And this is, of course, the second instance in the week, right? Where,
Yeah.
Yes,
Yeah.
indeed.
Yes.
We, in
Yes.
fact, had like 22. I just was reading in a newspaper, 22 flights also were cancelled, like to and fro to Bangalore. So it was not that easy for commute, at least on a commute purpose.
Right. And we didn't want people landing up, let's say, at 7 a.m. or 8 a.m. in Bangalore and not being able to find a cab and all of that. So just keeping that in mind, I said we just move this online. But yeah, so we just have to make do with I guess with what we have here. So right.
I thought of taking my car from here to there all the way. And then I realized that if I stuck at
coming
Bangalore,
from
then what would I do?
people coming
So
from
then
outside the Bangalore have no problem. People
Yeah,
coming from
especially
outside the
TN
Bangalore is no
registered vehicle.
because
Sorry, say that
we are
again.
so people coming outside from Bangalore have no
Hmm.
problem because we are coming yesterday. We
Yeah, but if you're
mostly staying in the hostel.
Oh, yeah.
if you're staying in
Mostly staying in
MTC,
the
then it's
hostel.
fine.
Yeah, if you're staying in the
Yeah.
campus, that is still okay, but
Then it's
outside
still
it
fine.
will be a problem.
But if you stay outside, and then if you stay, like, say, in the north
Outside
of
also
Bangalore,
most of the people are so outside most people are staying in the walking distance of the campus.
no, then maybe the
No,
people
it is
in
not
Bangalore
like
have
that.
a big.
I travel from for almost 15-20 kilometers and then reach the campus. It's not like that.
Exactly. So maybe people in Bangalore have a bigger
Yeah.
problem than the people
Outsiders.
staying outside Bangalore. So,
Indeed,
but
yeah, 20 kilometers for me as well.
what we don't want is a situation where you're coming here and then you sort of get stopped by a mob or by something else that happens, and then you get yourself into trouble. Then dealing with that issue becomes more critical than uh, and luckily for us, because we have Zoom and we have technology, we can sort of avail this, right? I mean, now having said that, is tomorrow okay for most people, or do you still want this to be
Yes.
online tomorrow?
We actually want to come to the class.
You want to come to class?
If it is okay for you in the hybrid model, then I think most of us are planning to come there.
No, so hybrid
But-
again is we would prefer to have this either completely online or I think completely in class. Are there people from outstation who have not come to Bangalore because of this?
Yeah.
Yeah,
Yes,
so,
yes.
so I have not.
Cancelled our tickets.
We have
We
cancelled.
can't.
Yeah.
Cancel.
Yeah.
Other way around, I traveled outside of Bangalore, considering this month.
I see, because so then that's an
Kids
issue as well,
have
right?
holiday, so I thought like at least come to my native, for since it's online.
Fair enough. Yeah, so that's another issue, right? Because then you don't want the same thing. That's fine. Okay, so we'll just keep it online for this week, and then hopefully there'll be no more disruptions after this. Again, although I mean, having said this, this has been a problem with Karnataka. I mean, this Kaveri water dispute is not going to disappear anytime soon, and so it's not, you keep having this over and over again. It's so disruptive to everybody else, right? I'm sure there must be a better way of finding solutions rather than closing down the entire city. I mean, that I don't think that helps anybody in any way. Fine. Okay. So having said that, so we will do this online today. We will pick up from where we left off the last time. I was nice enough not to give you guys an assignment. So, which, because
We were waiting for one.
Receive our assignments.
Recording
I
in
know.
progress.
So
And then
what
I said,
about
well,
the textbook? We also haven't got the textbook for business statistics.
not yet. Okay. I
Not
mean,
yet.
No.
not yet. Okay. Yeah. You're implying that my slides aren't good enough, Jyoti. Huh?
If we
I-
can get at least a link for the book, it would be helpful. Or if you can recommend, we can take it from library. If it is,
There is
in the course outline, you can see there's already a link for a textbook, and you can
Correct.
read it.
OpenStax.org. That book is
Yes.
wonderful. The link that you have given me, I'm loving. Like I read it and it's very helpful. And then there are questions to solve. I find it really nice way of practicing stuff. So yes.
Yeah, I mean, I think while there is a recommended textbook, and I'm sure we've ordered it and you will get it. I mean, if you had been on campus, I'm assuming this week you probably would have gotten the book. I'm guessing that the books are already here, right? Because they had told us that we would have it in, 15 days or so, and I'm sure the copies are here.
Yes,
But
correct.
having
Can
said
you
that,
collect it anytime? Come to the campus and collect it. Is it possible?
I think so. I'll ask Sharath to coordinate that with you, if that's okay.
Okay.
Yeah. But having said that, I think there's a lot of information that's available online, right? Access to information, I don't think is the problem here. If you just Google for, whatever topics we've covered, like for example, sampling distribution of the mean, you will get a million hits on Google, right? Right. But as I keep reminding people, having access to information is not the same as being educated. So, right? I mean, like having the textbook in your hands doesn't make us a statistician. No. So we have to sort of be able to apply what we are learning in the real world. Correct? So yeah, I will get you guys that textbook soon. Okay. So let me work with Sharath. I didn't realize that you guys didn't have it. Fine. Okay. Now, having said that, let me just sort of spend the first, 15 minutes or so recapping what we've done. Okay. So where we left off was broadly, what was our process that we followed? Right. So in terms of, guys, can you see my screen?
Yes, yeah, we're looking at it.
Do you see a blank PPT slide?
Yes.
No, we can.
Okay, so what is the process that we've broadly been following, right? So my setup was the following, right? I'm collecting some
Data.
yeah, I'm collecting some data. Correct?
Yep.
I use this data to sort of figure out how it looks like. So whatever maybe my random variable of interest in that data. Now remember that particular data set may contain many columns, right? So for example, my data set may look like this, right? So if I draw it in some ways, I have observations, which are 1, 2, 3, and so on. So I may have 100 or 1,000 observations. And in those observations, maybe I have collected many different things about a particular experiment. So one experiment could be, one particular thing, maybe the age of individuals, okay? Maybe I have 1,000 people and I've collected their age, like say 23, 46, and so on. Right? I've collected their income. Right? I have numbers here saying, 4 lakhs and so on. Right? I have all of this data with me. I have gender. I perhaps have number of members in the family. This particular person has 4 members in the family and so on. And therefore, I have all of this particular data, right? Is everybody broadly okay with me so far? Right. So I have this particular data set with me. And now let's say I'm interested in one of the observations that I have. You can pick any one of them, right? It could be age, it could be income, it could be any of these observations that I have collected. Guys, just to get a sense, is everybody able to see the slide that I have up there?
Yeah. We're looking at it.
Very clear.
Yes.
Yes.
Okay.
Sir, but you can be a little louder if possible. I don't know if you're farther from the mic or something.
I don't know if I can increase my mic volume. I can.
No, it is
Sure.
clear, quite clear.
It is clear.
Thank you.
Okay. Okay. Right. So suppose, and what did we do with this data? So I've now collected all of this data from a particular random experiment that I've conducted. And one of the first things that we saw was this notion of drawing a distribution, right? Remember, if I have, let's say, I'm looking at age of people in this particular experiment. So broadly, what am I saying? The column that I'm looking at is this guy. Can I draw a distribution for that data? What does that mean to you?
Yes.
What
We
does it
can
mean
have
when
a
I'm-
frequency.
How that data is very
Yeah.
spread out. Yes, that's the
How
word.
the age is spread within the pool.
No, those are numbers, right? What you're giving me are statistics. What I'm saying is like when I ask you to draw a distribution of this data, what does that mean? Can you draw a histogram? Is what I'm asking you.
Yeah.
Yeah.
Yes.
Yes.
So broadly, how would I draw
Frequency.
that? So
So,
We need to count the frequency.
exactly.
how many
Correct, yeah.
people at that age?
And before we do that, what would we do, Deepti?
On the X
Beginning-
would be the observation of the
Calculate
number.
the frequency of the people.
Choose the XY axis.
Identify the variable first.
For me, my variable is age. That's what I'm interested in. And once I do that, what would I do?
Calculate
the
bins and
Find the buckets,
I would
identify the
calculate the bins, right? Thank you,
Yeah.
Prerna. So one of the things that I would do is I would calculate the bins, right? I'm
Right.
taking that age bracket, and what am I doing here? I'm saying how many people are between the ages of say 0 to 20, 20 to 40, 40 to 60, 60 to 80, let's say. Let's say there's nobody else other than older than 80 in my sample. Okay, everybody okay with that? And then what am I doing?
Yes.
I'm
Yeah.
counting the number of people in the bin between 0 to 20. Correct? So, and therefore I will get something which looks like this. Right? Let's say there are whatever 160 people in our sample data set who are in the age group between 0 to 20. Folks, everybody okay with that?
Yes.
Yeah. And similarly, I have let's say something like this, which is there are 310 people between 40 to between 20 to 40, right? And then suppose I have the maximum number of people here between 40 to 60. Let's say there are 500, whatever, 400 people here. Broadly, everybody okay with that?
Yes.
Yeah. And then
Yes.
the remaining people, so you have already covered 710 and then the other 160. So 870 people are done. And therefore now I have the last bucket has 130 people here, correct?
Correct.
Right. This is broadly what I'm calling as a histogram, right?
Yes.
Yes.
This in some ways tells me what? It tells me the shape of my distribution. Right, I've drawn a diagram which broadly gives me some information about how my age groups are spread out in this particular data set. Everybody okay with me so far?
Yes.
Yeah.
The histogram in some ways also helps me answer some questions of probability, right? For example, if someone says, if I randomly draw an individual from the sample, what is the probability that they will be between the ages of 20 to 40? Right. So what is, again, let's be very clear about our notation here. What is X? This is my random variable, that is age of individual. Right?
Yep.
And someone is asking us what is the probability that this X value will be between 20 and 40. Right. And how do I find that probability?
You can divide 310 by 1000.
Exactly. Right. So what I'm basically claiming is that in my sample, there are 310 people in this age group. My total sample size is 1000. Therefore, 0.31 or 31% is the probability. So now if I assume that this sample is in fact representative of the overall population, right? Remember, I don't have data for the entire population. I only have this sample set of 1,000 people. But if I assume that the sample is reasonably representative of the overall population, I'm basically claiming that 31% of the population lies between the ages of 20 to 40. Okay? Everybody okay with that?
Yes.
Yes.
Right. Okay. Any questions so far? Okay, great. So
Not
if
yet. Yet.
right. Then what we also looked at was that look that if I'm used to drawing histograms like this, there were few other properties as well of this distribution that we started to look at, right? One, what is the mean? Right? Can I find the average age of all of my 1,000 people? Where would that be broadly? If I ask you, look at
Middle, somewhere in middle.
50.
Yeah, 40 to 50 maybe.
there's most, by the way, where is it skewed towards? Are there more people
Left.
beyond?
Left.
It's a little bit towards the, it's right
Left.
skew. The
Right.
distribution is
Right
right
skew.
skew.
Yeah.
No, as in
Right
there are more people towards the left side than there are towards the
Right.
the right side, correct? So I'm broadly claiming that let's say my mean happens to be somewhere here.
Yeah.
Everybody okay with that? So it will be somewhere there, right? So let's say in this particular data set, the average age of my data is 42 years. So far, so good?
Yes.
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 Right? Okay. So when I have 42 years as the average age, is that enough to, for example, tell me everything that I need about the distribution? If someone says that the age group has a mean of 42 years, the average
Yes.
age group, does that tell me everything about a distribution?
No.
Not
No.
really.
No.
No.
Not
No.
completely.
Why not?
It
Doesn't
can
give you the
estimate
spread.
It doesn't tell me the spread exactly,
Spread.
right? So
Yeah.
what I need now is something that tells me the spread of the distribution. Why is that important, by the way? Remember, we saw this example the last time where, you know, let's say I have demands in those stores. Did we give you this example? Right? So let's say I have store one, where my demand for a particular product is, remember, 49, 50 and 51, and where I have store two, my demand for a particular product can vary anywhere between 25 to 75, and I have store three where demand for that particular product can go from 0 to 100. Right? What is the mean of all demands in every store?
50. Same.
50.
Correct? My mean is still the same, right, for all my stores, but the variability in store one is much lesser than the variability in store three.
Correct.
Right? Suppose it's a perishable item, which means that I have to, whatever I don't use that particular day, I have to discard. Think of it like newspapers. Right? If I don't use newspapers on that particular day, then of course they're useless to me. I have to throw them away. Right? If I am managing store one, every day, how many newspapers will you order?
Minimum 49.
51.
51.
If you order 51, let's say, right? Or let's say I just order 50 as an example. Let's say my store one manager says every day I will order 50 newspapers. What is the worst possible outcome for that particular store?
One customer will
One
go back.
One customer.
One customer
one
may
extra.
be left.
Or one extra paper.
Or one
One
may
item
not
will
get, or one will be.
Precisely. Exactly, right? If my demand turns out to be 49, I will be left with one extra newspaper. If my demand turns out to be 51, I'm going to be left with one dissatisfied customer. Correct? But imagine following the same strategy here.
Yeah.
I may be left with 50 unused papers if my demand turns out to be 0, or I may be left with 50 dissatisfied customers, correct? You see the problem, whose job is more difficult here?
S3.
S3.
Both three, sir.
Absolutely, right? And why is that? Because my variability in demand is much more than the variability here.
Right.
See, S1 is what we would call as it's almost like constant demand, right? It's almost 50 every day. If it's almost 50 every single day, I don't need statistics. What I need statistics for is when, in fact, my variability is very, very high, right? When variance is high, and do we know how to calculate variance?
Yeah.
Standard deviation.
Yes, and well, standard deviation is the square root of variance, yes, but how do I calculate variance?
Variance is value minus mean.
Value minus mean. So if I was doing it for the last store, what would I do? I would do 0 minus 50 squared plus 50 minus 50 squared plus
100
minus 50 squared all divided by n minus 1, which is 3. 3 minus 1, that is 2, right? So basically what will I get? I will get a huge variability here. Whereas if I do it for store 1, I will have only, what is my variability for store 1? 1. It is 1 plus 1 divided by 2. So my variance here is 1, but my variability in the other guy is like 2500. Right? You see the huge, right? You see the huge difference between variability, and therefore it makes the job of S3 a lot harder. Right? By the way, in terms of our own, if you think of supply chain management and so on, S1 is basically what we would call, typically when would you find constant demand? You would call these as functional products. Have you ever walked into a store and found that they're out of toothpaste?
No.
No, why not? Very functional product, right? Everybody knows the demographics of the area that they're located in. Every supermarket will know approximately on average how many toothpaste they're going to sell. There's not that much variability in functional products. But if you think of innovative products like an Apple iPhone, right, then the variability is very, very high because it's very difficult to predict demand for a innovative product. Okay, everybody okay with that?
Yeah.
Right.
Yes.
So broadly, what do I need now? So if I have to describe a distribution, what I'm claiming is that look, that mean is not enough, right? I need variability. I need some measure of variability, and that is basically what I'm calling as variance, right? So even in this histogram that we've drawn here, I need not just the mean value of 42 years, but I also need variability, which tells me something about that particular distribution. Everybody okay with that?
Yes.
Right. And what is that variability? It tells me how spread out my observations are from the mean values. Correct? And once we figured out that, by the way, all of this was stuff that we've done in the first 5 classes, right? So, and once we figure out that I have a mean and I have a certain distribution that I need to be looking at, right? And a variability that I need to be looking at, I now basically came up with this notion saying we don't have to do this every single time. There are some standard distributions that we would look at, right? What are those standard distributions that we've looked at?
Binomial.
Binomial.
Normal. Poisson.
Poisson.
Yeah. Those are all discrete distributions, right? What is the continuous distribution? Like age, for example, is a continuous normal, right? That is broadly what we've been saying, correct? Right? We've looked at this distribution, which we basically are calling as the normal distribution, right? So what is my normal distribution? How does it look?
Bell curve.
It's a bell curve, correct? So I have a normal distribution which looks like this. I have my mean in the middle, mu, right? And and there are some properties of my normal distribution, correct?
Right.
What are those properties of the normal distribution? If I walk one standard deviation,
34%.
Side, 35% of the observations lie between one standard deviation.
How many?
68%.
8%.
68%. Correct. So there is, exactly. This is my 68%. 2 standard deviations would be what?
95%.
95.9.
What is the exact value? Is it 2 standard deviations?
Yes.
1.96.
1.96 to be precise. Yeah. So if I walk away 1.96 standard deviations to the left, and 1.96 standard deviations to the right, then I would have like
95%.
95% of it. Exactly, right? These
Yeah.
are all properties of the normal distribution that we've already seen, correct?
Yes.
Yes.
No. Then when we look at this particular normal distribution, if I compare two normal distributions, okay, if I compare two normal distributions, let's say with the same mean, but let's say I have the same mean mu, but its standard deviation is wider or bigger. What does that mean?
Variant.
There is a larger spread out of the data.
There's a larger spread out of the data, exactly. And so if I had to superimpose the second normal distribution on top of this, what would happen to that particular normal distribution?
It will flatten.
Yeah.
It
It'll
will
be flatter. So which means that what?
Variance will be
mu,
more.
At the mean, at the central point, will its height be higher or lower?
Lower.
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 Right? So then you're basically looking at something that looks like this.
Yes.
Correct.
Yes.
Guys, yes?
Yes.
That is basically a normal distribution which has a higher
Spread out of the data.
Higher variance.
higher variance. Sigma is more. Sigma 2 is more than
Sigma 1.
Sigma 1, right? The first normal distribution had a standard deviation of Sigma 1. I'm claiming that the second one is more spread out. Everybody okay with that?
Yes.
Yes.
Right. Which brings us to, if everybody remembers this, then it broadly brings me to this notion of, can you guys see my PDF?
Yes.
Looking at it, yeah.
Yeah, okay. Which is broadly what we were looking at, right? We started with this notion of, once we had done some analysis of the normal distribution, we started looking at what was called the sampling distribution of the mean. Right? Do you remember this?
Yes.
Vaguely.
Yeah.
Yeah.
You all want the textbook, but we've not seen the slides. No? Like, what is that? What is the sampling distribution of the mean?
Mean of
X bar mean.
And samples. So each sample has its own mean.
Each sample has its own mean, yeah.
The distribution of those means.
It's the distribution of all of those means, exactly, right? So then, how does that look?
Like a normal distribution.
Normal distribution.
Almost, yeah, that's true. Well, it looks like a normal distribution when?
It's closer in. Many means put together.
And the population, when n greater than 30.
When n
sample
is greater
size.
than 30. That's the answer.
Almost.
Yeah.
Right? So, what did we say? Well, what we are asking here is, what happened here?
Or if your population is normally distributed.
What I said was, well, I took a sample from a distribution. I calculated the mean. I called it x1 bar. And that is from my first sample. I've got a sample mean. Then I did the same for
another sample.
I did the same for another sample. I called it x2 bar. And now I'm looking at the distributions. If I take 1,000 samples, I will have x1 bar, x2 bar up to x 1,000 bar. Yes, everybody okay with what I'm saying here?
Yes.
Yeah.
Right. So what am I saying? So remember, when I went back to this particular example that I have here, these 1,000 observations that I have are what I am calling as my sample 1. The average age turned out to be
42.
42.
That
For
is
one
the
sample.
first sample mean
Sample.
that I have. This 42 is what I am calling x1 bar. Everybody okay with that?
Yes.
Imagine that I have now another sample of 1,000 observations and I calculate their average. I will call that x2 bar. and similarly sample 3 and sample 4 and so on. So now I have samples of averages of age, right? So
Mean of all the samples.
I have x1 bar, x2 bar, and so on. Now all the way up to, let's say, some x1000 bar.
Yeah.
All of these are means. Correct? This
Yes.
one was obtained from its own sample of 1000.
Yes.
Yes.
X2 bar was also obtained from its own sample of 1000 and so on. Right? When I draw a distribution of these guys,
Okay.
remember now I have 1000 numbers. I'm calling them x1 bar, x2 bar up to x bar 1000 or whatever, right? So if I draw a distribution of these guys, that is basically what we are calling as the sampling distribution of the mean, right?
Yes.
Okay, and when we do this, what am I getting? What was our conclusion? Our conclusion was what? That as the sample size increases, my distribution starts to look more and more like the
Bell curve.
Bell curve.
Yeah, right. So in the example of age that I was talking about, what is the sample size?
1000.
1000, exactly. Right, that sample size was 1000. And what I'm claiming here is that if the original distribution, if age was, if the original distribution of age, what did we, if age was distributed normally, let's say with a mean of 42 and a standard deviation, let's say of 10 years, my mean age of the sample is
42.
42 years for that particular population, and let's say the standard deviation is 10 years. My sampling distribution of the mean will be what? It will also have the same. It will have the same mean, yes, but
Standard deviation
but its standard deviation will be reduced by
root n,
sigma over root n, where n is what?
number of samples.
Number of sample.
No, it's not the number of samples. It is the size of each sample. Remember?
Oh, yeah.
Okay, so suppose I have every sample has like 1000 observations. This n is 1000 now.
Yeah.
Okay.
It's not the number of samples that I'm collecting, but it is
Number of observations in
Observation
each
inside the
each
sample.
sample. Exactly. Just be careful. Okay, so it's not the number of samples, right? So what I'm claiming here is this standard deviation will now become 10 divided by square root of
1000.
1000. Will this distribution be more narrow or wider?
Narrow.
Narrow.
It will be narrow, right? This is very narrow as compared to
The previous.
this guy.
Original.
That's the original distribution. Right. Basically, what am I saying? That as the sample size grows, we regress towards the mean. Right. So it becomes narrower and narrower. If my sample size was larger, it would have looked even more narrow, right?
Yeah.
Right. I'm basically coming closer and closer towards the mean. Okay. Everybody okay with this notion of the sampling distribution?
Yes.
Right.
Left side is population distribution or sample distribution.
Sorry?
Left side is population distribution or sample distribution.
This is the population. If the population is normally distributed with a mean of 42 and a standard deviation of 10, my sampling distribution of the mean will also have the same mean of 42 years, but its standard deviation gets divided by the square root of 9. Yeah. Yeah. Somebody had a question?
Sample, we are saying 1000 sample for the first one, right? Here it looks like a bell curve, but we do not know what the sample would be for the others, right? Are we assuming that it'll all be normal distribution when we take many samples, like X bar we are here saying as 42? The other samples could be different. The X bar could be 60 or 70 or 80. We do not know. So I'm not able to understand why all of them can be assumed as bell curve.
No, we're talking about the population, right? If the population overall was normally distributed with a mean of 42 and a standard deviation of 10, then my sampling distribution of the mean would have the same mean and its standard deviation would be divided by the square root of n, right? So for example, in the slides here that I had, my original thing was not normal, right? Remember, I was looking at the toss of a
Point.
die.
Nice.
If I looked at the toss of a die, my original distribution had 1 by 6, 1 by 6, 1 by 6, correct? It looked flat, no, like this, like what I have on the left hand side.
Yeah.
That is not normal. This is the original distribution of X on the left hand side. But when I did samples of 2 and I took their average, it turned out to start looking like the normal distribution.
So does it mean that irrespective of the population, distribution, the average of the average of these would look like a bell curve?
Exactly. As the moment your sample size starts to cross 30, irrespective of how the original population looks like, I don't need that to be normal.
Okay.
If the original distribution is normal, then even if my sample size is smaller than 30, my sampling distribution also would be normal. But if the original population does not have a normal distribution, then I need at least a sample size of 30 or more to make my sampling distribution of the mean look normal. Yeah.
How did we get this 30 value? Is it a known
empirical value? So this 30 is only empirical value, right?
It's broadly a rule of thumb. Yeah. I mean, if you start drawing it,
error
right,
calculation.
See, you see here also, correct? Even in the slides that I have, the moment I start getting close to 10, my original distribution was flat. Right? It was all 1 by 6, 1 by 6, 1 by 6. But the moment I start to get a sample size of 10, does it start to resemble the normal distribution?
Yes.
And then the moment it becomes 30, right, it will almost be the same as a normal distribution. Everybody okay with that?
Yes.
Why do I need this? Yeah, because remember this example?
Yes.
What is this example asking us? Saying that, look, that you have a Coca-Cola bottle, right? The label on that bottle says 32 ounces, right? But in reality, they fill a little more. Okay, the mean is 32.2 ounces and a standard deviation of 0.3 ounces. Right. And the question that was asked is, if a customer buys one bottle, what is the probability that the bottle will contain more than
32 ounces.
Okay. How would we do this, by the way?
Mean plus 2 standard deviation, which will have a 95% of chances that it will be.
No, hold on. Right. So if I open up Excel, what is my formula?
1 minus normal distribution.
Okay. Suppose I ask, don't worry. Tell me, see, I'm a customer. I am buying. Let me see if this works. Yeah. I hope this works. Can you see me drawing on the Excel sheet?
Yes.
Is it clear?
Yes.
Yes.
Yeah, it is clear.
Okay, so I'm told that I have a Coca-Cola bottle which is normally distributed with a mean of 32.2 ounces and my standard deviation. So this is mu. Right? And standard. And my standard deviation sigma, stopped writing, I don't know why. Okay, standard deviation is 0.3. Correct?
Yes.
Yes.
Suppose I am a customer who buys. Let's say I'm a customer who buys a bottle, right? I buy one single bottle and I say, what does the bottle say? The label on the bottle will say
32
ounces is not
the label on my bottle will say what?
32 ounces of
32.
soda.
It will say 32 ounces, correct? I don't know why it's not writing it. Okay. It will say 32 ounces, correct? Now I buy one bottle and then I say I'm going to measure. What is the probability that the bottle will have less than 32 ounces? How would we do this, guys?
Norm distribution.
Yeah, so I would use one.
Yeah.
I'm a customer, I've bought. Can you guys see the formula that I'm typing?
Yeah.
Yes.
Yeah. So what will I do?
Normal
On this what?
32.
32.
I will do 32 ounces, right? So that is basically
Mean
what I
is
want.
32.2.
My mean is 32.2. Yeah.
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 Deviation is
0.3.
0.3.
So
0.3.
standard deviation is 0.3 and
True. False. False. True.
Okay. Basically, what will this give me? This is going to give me,
Area under the
what is that?
Area under the curve.
So what is this saying? This is what?
probability
25%.
25%.
25%, right? So this is what almost. So what is the thing? What are we saying? I bought a bottle,
Less than 32 ounces.
right? So I bought something. I'm checking for the area before.
32.
Yeah. So this is the area less than 32 ounces. And I would, by the way, imagine if you're a customer, you buy a bottle of Coke and there is a 25, and what is that bottle of Coke supposed to give you? It is supposed to give you 32 ounces of Coca-Cola, right?
Correct.
But there is a 25% chance that that bottle will actually have
Less.
Less than
32
32 ounces.
Right. So is that good for the customer?
No.
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 No. You're basically like, what do you think these guys are going to do? They're going to sue, right?
Yes.
Right. No.
Health wise, it might be good for the customer.
Right. Right. So, I mean, the United States is a litigious society, no? So then what am I going to do? This customer buys a 32 ounce bottle, finds out how much Coca-Cola there is actually is in the bottle, figures out that there is 25% chance that which means what? That 1 in 4 people that are buying are actually getting less than
32 ounces.
32 ounces.
That's not great for Coca-Cola, by the way. Right. What is their answer?
Buy more. Buy a pack.
By 4.
By
Buy a
4,
pack.
there
Right.
is a chance in getting
Increase the
32.
sample size.
What are they saying? Their average is 32.2. Right. Some bottles are going to have lesser, some bottles are going to have
More.
If you buy a 6-pack or a 12-pack of Coke, it is going to average out, and on average, you are going to get more than 32 ounces.
Correct.
Right? Does that logic make sense?
Yes.
Yes.
So now, if someone buys a 12-pack instead of buying only a single bottle, right, what is happening to my distribution? Now, what am I looking at now? I'm looking not at a single bottle, but I'm looking at
6 bottles.
Pack of 6.
I'm looking at an average of
6 samples.
12 bottles, right? So now I have a normal distribution.
5 minus by root 12.
I have a normal distribution where my mean remains
32.2.
32.2.
My mean remains 32.2, but my standard deviation of this guy becomes what?
0.3.
32.3 divided by under root of
0.3 upon under root of 6 or 12.
No, 12.
Right? I bought a 12 pack, let's say. My standard deviation reduces to 0.3 divided by the square root of 12. Is the standard deviation bigger or smaller than the previous one?
Smaller.
It's smaller, which means that this particular normal distribution is narrower than the other one.
Correct.
Which means there are more observations closer to
Mean.
mean, 32.2. Does that logic make sense?
Yes.
Right. If there are more observations closer to 32.2, then broadly, what is this guy telling me? Now, if someone buys a 12 pack and says, what is the probability that, like, I'm going to get less than 32 ounces on average? What is that going to be? That is long list what?
32.
Till 32.
32.2.
Mean remains 32.2.
And standard deviation reduces by
0.15.
Standard deviations becomes 0.3 divided by square root of
12.
12, correct? And then
True.
True.
Correct.
now okay. Now what am I claiming?
104%.
1%.
1%.
1%.
There is only a 1% chance that on
Okay.
average you will get
Less than 32.
Less than
32 ounces. There we go. It's a huge drop, right? From 25%.
1%.
The chances that I'm going to get less than 32 ounces has dropped to
1%.
1%. You see the difference between buying one bottle versus buying
12
12
bottles.
bottles.
12 bottles.
What incentive is there for Coca-Cola to cheat you? Right, by giving you lesser than what they are printing on the label. Nothing. What are they going to gain by cheating you out of that 0.1 ounce of Coke? Right, because for them a lawsuit is far more expensive than giving you that extra 0.1 or 0.2 ounces of Coca-Cola. You see where I'm going with this?
Yes.
In fact, they give you a little more, right? On average, they're giving you 32.2 because they're factoring in that if you keep the bottle for a long time, there'll be some evaporation, there will be, some loss somewhere or the other, and so on and so forth. They're actually on average giving you a little more than what you're paying for. Okay,
Then
everybody
we
okay
have
with
to
this?
buy 12 bottles for that.
On average, broadly, what are they saying? That look, just you cannot sue the company based on one sample point.
Yeah.
By just buying one bottle, you cannot sue the company.
The number of observations should be more.
Right? Buy a few and then make your conclusion. Are they really cheating you or not?
Yes.
Right?
But then
Does
also
that
it is
make
not
sense?
proving, right?
Sorry?
Then also it is not proving. If we buy more, the
Yeah.
mean remains same and standard deviation reduces, the probability reduces. It's more chance that we can sue.
No, not really. The chance
No.
that you're going to get less than 32 ounces is like now just 1%.
Yes.
Okay, less. Yeah.
Yeah,
So
Sandeep, it is less than not.
it's less than, yeah. So the chances that you're going to get less than 32 ounces is just 1%, right? In fact, if you buy 100 bottles, that chance is going to just disappear.
Yes.
It will never be 0%, right? It will be nearby 0%, but not.
Thinking it other way.
Of course,
Say
yeah.
for
It
every
can't
bottle I'm
be
giving
zero.
about 0.2 ounce extra.
It can never be zero. I mean, is it possible that out of 1 million bottles, like, there'll be one that may have this thing? Of course. But that's not enough to sue the company and say that, look, that they're cheating customers. Okay, that chance, if I buy like a pack of, 24 bottles or whatever, then this thing standard deviation starts getting smaller and smaller, and therefore, like, you'll get regress towards the mean, no? Srihari, does that answer the question?
Yes.
No. My question was, if I want to make, not zero filling, if I do not want to deviate, like what should be my standard deviation so that I can bring down this 32.2 to 32, narrow to 32.
No. 32.2 is the mean that is given. They
And
are on
ideally, I'm
average
supposed to give
filling.
only 32.
Sorry?
Ideally, I'm supposed to give 32. That is what I have put on the label. But still to coverage this variation, I'm giving 32.2 as a standard and normally
Correct.
distributed over this. Now, to reduce this 0.2 extra water I'm giving.
Yeah.
Okay. Can I narrow it down to 32.1 and still my variation is less than this? So what should be my standard deviation? I mean, I don't know how do I pose my question.
No. So my standard deviation is going to be whatever, like it's dependent on the sample size that the customer is buying, right?
So if I make my process stringent, no, sir, I can make, by increasing making it more narrower.
Of course.
even if I buy one bottle, it can be still 0.2, 25%, and 4 bottles still can be 10%. Though average is 32.1. Can I do that?
Of course. But then let's hope to maintain the same proportion. Your standard deviation, which is now 0.3, must now become 0.1, right?
Reduce the standard deviation.
But how do I do that?
Why do I have a 0.3 standard deviation? Because at the end of the day, whatever machine is filling those bottles is a precision engineering machine, right? It has some variability. If that machine becomes more and more accurate in filling, right, I will be able to fill exactly closer to 32 ounces. It's just that, like, you want to give yourself a little bit of a buffer, right? There is some precision engineering that happens in that particular machine. It has some fault, right? And therefore, you're giving yourself a little more leeway by filling more.
Understood.
Yeah, Samir?
How do I calculate my standard deviations for that? I'm just
Try and error. Try, no. Keep the same percentage. Try for 0.3, 0.25, and so on, and see where
you have to make a trial, right? Okay.
Yeah. Samir?
Okay. Okay.
So you said there was a statement that more than the size of the sample gets increases, it more looks like a bell curve, right? And then you add some number of 30, as in more than 30 samples, it would it starts looking like. Where this number 30 is coming from? Is there any notation for that?
So we haven't got into the T distribution, but broadly that's where it comes from. Okay, so there are some, when the moment your sample size crosses 30, again, you can verify this by drawing a diagram as well, right? Your distributions will start to look more and more, they will approximate the normal distribution. Right, you want to get as close to the normal distribution as possible. So, which is why I'm saying that when this is something called the notion called the degree of freedom, we haven't gotten there yet. Right, but when the number of degrees of freedom of a distribution gets close to 30, that distribution starts to look like the normal distribution. Okay.
Okay.
That's fine. Just hold off on that thought. Yeah. Don't worry about it. Just use it as a rule of thumb. No? Okay. Yeah. There's somebody else who had a question. Somebody else had a hand up and they took away their hand.
Yeah, sir. Sorry. I just a thought that if we are applying the stats observations to the population, then I would obviously be on the much safer side, I would say. For example, if I, from a company's perspective, if I want to check how many, what is the probability of printing out or making out a bottle which has less than 32 ounces. So if I applied it to the whole population, then my whole graph will be much more spread, right? So if I say taking out 1,000 bottles from that sample, if I say there is a 20% probability that there is less than 32 ounces, but that is not correct, right? If I applied it to the population, the area under the graph would be drastically lower than what I am getting with the 1,000 bottles.
Sorry, Siddharth, I did not understand the question because what you are comparing is the original graph, which had 32.2 ounces mean and standard deviation of 0.3, is a distribution where I'm taking one bottle at a time.
True. And I'm trying to implement it to the population. See, from a manufacturer point of view, if I produce 1,000,000 bottles, then I have this sample size of 1,000, which tells me that the probability of getting less than 32 ounces may be 20%. But if I, from a manufacturer point of view, the probability of getting that a bottle less than 32 ounces will be much lower than 20%, right?
Why is that?
Because if I increase the sample size and apply it to a population of 1,000,000 bottles, right, the graph will be much more flatter. So at the same point, calculating the area under the curve for the much more flatter curve will be
No,
lesser.
sorry, hold on, Siddharth. So I don't know what it is that you're doing. So if I take a sample of 1,000 bottles from a population of 1,000,000,
yes,
I am calculating their average amount of quantity in the bottle. Correct?
If I'm right, Siddharth is trying to connect that we started learning first from the population. We will take a sample, a group of sample, and based on our findings with sample, we apply that kind of understanding for the entire population.
Like,
so, is that right, Siddharth? So in that case, in this smaller sample set, what we are seeing, less than 32 ounces bottle, what we are going to produce. So in terms of the entire population, again, we will see the quantities will go proportionately same, and then our curve goes much flatter.
No, but the assumption here is our sample size will reflect the population.
Yeah, that is
And
what we are
making a random selection, though
Yes.
the population size increases, the result will almost remain same. And the probability of change, like from 32 to 32.2 to 32.1, is very less. Or even 32 will be very less. That is what the random size, sampling will help us in selecting it, correct?
By the way, just so we are clear here, in this particular example, I'll get to you, Sandeep, 1 second. Remember that what am I saying? In this particular example, what are we told? This is not for a sample. Right? I'm told that this is
For the population.
it's for the population, right? My population is normally distributed with a mean of 32.2 and a standard deviation of 0.3. Okay, we are not talking about a sample. We are talking about the overall population. Okay, so let's assume that we have that information for now. Yeah, Sandeep?
Yeah, so my question was on the population, if it is not normally distributed, but the sampling means and the means distribution is normally distributed. That's the rule of thumb I learned today. But can I apply that? For example, I try to look at if I send approval to 4 or 5 approvals in my organization, 3,000 instances I have a data. Yeah, how much time it take for them to approve? So 3 days, 4 days, 3.5 days. So I have that data, but it is not normally distributed. But if I take mean and raw sampling distribution, that will definitely a normal distribution is what can I apply in this situation?
Yes, that is correct.
Okay.
As long as your sample size is more than 30.
Okay, that's another thing. Understood.
Correct. I can't use only 5 employees because then it will not look close to normal.
Yeah, yeah.
Okay, but if I take sample sizes of 30 or above, then yes, then you will get a normal distribution.
Yep, thanks.
Yeah, Pramod?
Hey, so just 2 questions. One, so 32.2 and 0.3 are population parameters, right?
That is correct.
Like from that we are deriving your sample parameters, but practically like you won't know population parameters. You'll basically know sample. So, I mean, is that like how do you get in real life 32 and 0.2 and 0.3, right? Like because that's something which we would have to estimate.
Exactly. So which is the reason why, because you don't know the population parameters, you will use what is called the T distribution, which we will do today.
Okay.
You cannot use the normal distribution. You will end up using something that looks like normal but is not normal, which is what we are calling as the T distribution.
Got it.
And that is based purely on sample parameters. It is not based on population parameters.
Got it. So the second thing is, if you take say like 1 million sample size, 1 million population, 1,000 sample size, say of your population, sigma is your standard deviation. Your standard deviation of your sample size will be sigma by root of 1,000. So say that whole sample becomes 1 million.
Sorry, no, that's not true. I draw a sample of 1,000 from a population of 1 million.
Right.
Right. Now, my
it's the other way around. Okay.
That is the average of the 1,000 is going to be sigma over root n. The sample itself will share if the sample is representative of the population, it will have similar characteristics to the overall population. Its mean and standard deviation will almost be the same as the population. But what I'm talking about is not the sample, this thing. I'm talking about what? The average value of that particular sample. Remember, this is the sampling distribution of the mean, not of the sample itself. Okay?
Yeah, thanks.
Everybody okay with that? Yeah?
Yes.
Okay, cool. And therefore, what we ended up getting in this particular example was that this thing sort of reduces, right? So there is in this case, they took a sample size of 4, right? And what happened there was that 25%, which is the orange region that you're seeing in the top graph, basically now reduces to 10% when the sample size is 4, and it reduced to 1% when the sample size became
12.
12. Exactly. Right. So the more the number of bottles you buy, because
The
most
less.
of them will have 32 ounces or higher. Right. Remember, half the bottles will have more than 32.2 ounces. Right. How many bottles will have more than 32?
Half of that.
No.
75%.
25% have more than 32 ounces. Remember?
75%.
More than 75.
75% exactly has more than 32 ounces. You can see that in the green region in the top graph, right?
Yes.
Yes. Yes.
So 75% of my bottles have more than 32 ounces. So then, you know, as I keep buying more and more bottles, the chances that the average of all those bottles will have less than 32 will keep dropping. Does that make sense?
Yep.
Yes.
So
Yes.
here we are
Yes.
taking X is 1. For one bottle, we are just seeing the percentage is 75%.
Correct.
And then as the sample increases, the chances of getting less than 32 will be very narrow.
Very narrow. Absolutely.
Yeah.
Right?
Yeah.
Okay. So, and then we saw this example, no? The one where we started to say, well, not just sampling distributions of one particular population. Can I now do sampling distributions of more than one population, right? Which is basically where we were, correct? So what I said in the last thing was the following, and this is broadly where we stopped. Okay, what was our conclusion here? That if I have a normal distribution, stop. Sorry, my pointer just stopped working and I don't know why. Okay, fine. So
it's a draw with touch.
No, it's draw with touch, and I have actually a pen which is supposed to work with this laptop and it stopped working. My finger works, but the pen doesn't work. Okay, fine. So I'm drawing with my hands. These are technological glitches that don't happen when I'm in a classroom.
Right.
In fact, after 2 years of COVID, when we started going back to having fully offline classes, one of the first things that I did in front of my students was I went and hugged the blackboard because I missed it so much. This is an integral part of my life, and unfortunately, I missed it for 2 years. So I went
No,
and
but
hugged
there
them.
is a rule in IT, at least, whenever you are to present something, when you have big webinars and hundreds of people are listening to you, whatever can go wrong will go wrong on that particular occasion.
I know. Yeah, that's Murphy's law, isn't it? So, right. Okay. So what is this? What am I claiming here? That if I have two normal distributions which look like this, when I add them up, right? So when I add them up, what does that mean, by the way? What does it mean when I add two distributions?
Sample size will increase.
No, there's nothing to do with sample. I'm just talking about what is the addition of two distributions. What does that mean?
I add every distribution, every item in the distribution I add.
So let's say I draw a sample of, like, say, 1,000 observations from the first distribution, and I draw a sample of 1,000 observations from the second distribution. I add them up. I add up those two columns. Can you sort of imagine that? In Excel, I have.
The mean will move.
Yes, of course, the means will move, right? So what am I claiming here?
Sample of 2,000 distributions.
Okay. So what I'm basically saying is the following, guys. Okay, so what I'm asking you to do is this. I take 1,000 values from here.
Right.
I take another 1,000 values from here.
Yep.
I just add them up.
2,000 values. The sample becomes bigger.
No. I'm not mixing them. I'm adding.
Adding. Okay.
I'm adding. I'm not. Folks,
Mean will shift.
You have a third sample or something?
No. So I'm just adding them up, which means I'll have 1,000 observations where I've added them up, right?
Mean remains same.
Mean will get added.
Okay, let me do this again, right?
Means
Let's
will get
say,
added.
guys, hold on for a second. So let's say this is the first observation that I took from here. Everybody okay with that?
Yes.
Yes.
Then I drew one observation from the second one. Let's say this guy turned out to be the first observation that I got from here.
Okay.
I add them up. I add those two values. Everybody okay with that?
Yes.
So then I take a second observation from here. I take another second observation from here. I add those two values up and so on. Now I will have 1,000 observations where I've added up, right?
Yes.
That distribution will look like what? It will also be
Normal
normal.
distribution.
Normal distribution.
Normal distribution.
Its
And the mean will
be
be the combined addition of the two things.
exactly. It will be mu1 plus mu2.
Mu2.
Right? But its standard deviation will be what? It will be sigma 1 squared
Plus sigma 2 squared.
plus sigma 2 squared. Okay. Everybody okay with that?
Yeah.
Square
Right.
root also, right?
Square root and
Yes.
divide by.
No. Not yet.
This is
for the
normal
population.
distribution.
Okay, so if this is the population, I can add two populations by, and then the overall mean of the additive normal distribution will be mu1 plus mu2, and its variance will be sigma 1 squared plus sigma 2 squared. If I subtract observations, what will I get? I'm going to get a new distribution whose mean will be mu1
And minus mu2.
minus mu2, but the variance still remains
Same.
sigma 1 squared plus
Yeah.
sigma 2 squared. Okay, so variance doesn't change. Variance will continue to be additive, but the mean will become like we will subtract
It is the difference.
the difference of the two. Okay, everybody okay with that?
So can I
Is
ask
that,
you a question?
is that concept sort of clear?
Yeah.
Suresh, yeah.
Sir, I have a question.
Yeah.
For any normal distribution, is it correct to assume that the mean, median, and the mode will be the same?
That is correct.
And this
Yeah. Sorry.
I have a question. So on this addition, is it true only for normal distributions, right? How can we add any two distributions?
No, we're sticking to normal for now. Okay, so I'm just talking about normal distributions. When I add two normal distributions, the resulting distribution will also be normal with a mean mu1 plus mu2 and the variance sigma 1 squared plus sigma 2 squared. Okay, and similarly for the subtraction part of it. Okay. Now, why did I do this? Yeah. Okay, is everybody sort of okay broadly with this? Sorry, with sums of normal distributions. Are we okay with this?
Yep.
Yes.
Right? Yes. Okay, so now the reason why I did it is because when I don't want x1 plus x2. What I want from you guys is this guy.
Can't hear you. Is it only me?
Sorry. Let's say this is the sampling distribution of the mean. This is x1 bar. This is not x1, but this is x1 bar. Is that normal?
Yes.
Yes. Correct. So its mean will be the same as the original mean that we had, which was mu1, but its standard deviation gets divided by
Root of n.
Root of n, right? Everybody okay with that?
Yep.
Yes.
I now have the second one. This is x2 bar.
Yes.
Same story. I will have mu2 here, but its standard deviation will be sigma 2 over
n.
Okay. Let's call the sample size different. Let's call this n1 and n2 as well. Now, when I add up x1 bar plus x2 bar, what am I getting? Apply the same logic that you used before. I will get a new distribution which is normal, but its mean will be what? Its mean will be mu1 plus mu2.
And standard deviation is sigma 1.
I can't directly add. I can't directly add standard deviations. I have to add variances. So therefore, I will get sigma 1 squared over
N.
N1 plus
Sigma square
over N2
N2.
square.
No, there's no square. Its mean is mu1 plus mu2. Its standard deviation is this guy. Folks, everybody okay with this?
Yeah.
Just a
That's
short
variance.
brief
That
of
variance.
why we want to do this. Is it only in practical purpose? It is only to have the comparison of two normal distributions. When it is combined, to have how the data looks. Say, for example, I'm comparing Delhi and Bangalore city, and then these two data sets, and then as an overall these two cities, how the data looks. This is how we are trying to do with this.
No, we are doing some calculations on them. So suppose somebody comes and says that, let's say I'm comparing salaries of people in Delhi and Bombay. Everybody okay with that? Let's say I tell you that the salary of people in Delhi is normally distributed with some mean and variance. Salary of people in Bombay is distributed with some other mean and variance. Does that logically make sense?
Yes.
Yeah.
Okay, so in this example that I have here, let's say the first distribution is Delhi. The second distribution is Bombay. Folks, everybody okay with that?
Yeah, yeah.
Yeah.
Right? Now, suppose someone comes and says that, look, that people in Delhi make more money than people in Bombay. Right? Everybody okay with that?
Yeah.
Right. So, but is that, so broadly, what am I asking here? Suppose someone comes and says, the example that we did, remember that example of those Columbia and NYU salaries that we were doing?
Yeah.
Yes.
Yeah.
Yes.
Right. So that is broadly where I'm leading up to, right? Because now I'm comparing, saying, suppose somebody comes and says, if I pick up a random individual, one individual from Delhi, everybody okay with that?
Yes.
Yeah.
And I pick up one individual from Bombay, what is the probability that the person from Delhi makes more money than the person from Bombay? Are we okay with that?
I'm a bit confused here of why are we adding, to be honest.
Sorry?
I'm a bit confused of why are we adding here, because that's what we've been discussing, right? So even in this example, where are we adding?
No. So we are, in this particular example, we are subtracting. Okay. So, okay, let me say this, right? So what is X1? X1 is the random variable that measures salaries in Delhi.
Yeah.
Okay. X2 is the random variable that measures salaries in Bombay. Guys, everybody okay with that?
Yeah.
Let's say this mean, just to put ourselves number, let's say this is 40 lakhs. And let's say this is 38 lakhs. I've drawn a distribution of salaries. My mean for Delhi turned out to be 40 lakhs. My mean for Bombay turned out to be 38 lakhs. Guys, everybody okay with that?
Yes.
Yep.
Okay, let's say this standard deviation for Delhi is whatever, 3 lakhs. And let's say this guy is 4 lakhs. That's how my histogram looks like. I took a sample or whatever it is. For Delhi, my population is, let's say, normally distributed with a mean of 40 and a standard deviation of 3. For Bombay, it is 38 with a standard deviation of 4. Guys, everybody okay with that?
Yes.
Yeah.
Yeah. Okay. Now, suppose I take one person from Delhi and one person from Bombay. What is the probability that the salary of the Delhi guy is going to be more than the salary of the Bombay guy? What is my question? I take
40 minus
one
40.
person from
Bombay.
Delhi and one from Bombay.
Person
I
from
take one person from Delhi, one person from
One
Bombay,
person from Bombay.
and I'm asking what is the likelihood that
Delhi
the
guy.
Delhi person makes more money than Bombay.
What is the value of N1 and N2? Is the population same we are considering, or we are considering it different?
No, Vatsala, remember, in this case, if I draw one person from Delhi and one person from
One
Bombay,
person only. Okay,
N
N
is
is
1.
one. Okay, okay.
N1 is 1 and N2 is 1.
ठीक है.
I don't care about the population, I care about my sample size. Right? How many observations am I drawing from that sample? Okay, so what am I asking? Yeah, so if X1 represents the Delhi salary and X2 represents the Bombay salary, what am I saying? I want the probability that X1 is more than X2, correct? Everybody okay with that? I've drawn one random person from Delhi, one random person from Bombay. This is what I want. Is this the same as writing the probability that X1 minus X2 is
Greater than
more than
0, right?
There we go. Now I have subtracted two normal distributions. And what am I claiming about that distribution? X1 minus X2. It will have a mean mu1 minus mu2. Its standard deviation or whatever its variance is going to be sigma 1 square over
Variance
n1.
is 5, mu is 2.
And it's sigma 1 squared over n1 plus sigma 2 squared over n2. But because I've drawn only one person from Delhi and Bombay, n1 and n2 are both equal to 1. Therefore, I can just write this as
9 plus 16.
Now, can I find that probability using norm dist?
Yeah.
Yes. Yes.
Everybody okay with this? What is mu1 for me?
40.
Mu1 was 40. Sigma 1 was
38.
3.
Sigma 1 was 3.
3.
Mu2 was 38.
Yeah. 38, yes.
Sigma 2 was
4.
4.
Now, can I find norm dist of that guy? With these values, this is my mean, that is my variance. Can you find the probability that what will that value be? I want to find in my Excel, what will that be? That will be norm dist.
2.
What value?
0,
0. Yeah, so 0 is what I want to find. Mu1 minus mu2.
2.
Standard deviation is sigma 1 squared plus sigma 2 squared square root.
25.
Right? So,
25.
In Excel, I have to use standard deviation. So therefore, that will be. This is variance, remember?
Correct. Square root of
yeah. And square root of 25 is 5, no? If you use this formula in Excel, you will get the probability that a randomly selected person from Delhi will have more salary than a randomly selected person from Mumbai. Folks, everybody okay with that? How much is that value? Can you guys give that to me?
34.45.
2.07.
Sorry?
34.45%.
34.45%.
In this case, it should be inverted area, right? Because we are looking at the difference greater than 0. What we found is less than 0.
Oh, it's less than 0. Yeah. So then you guys should be doing the other one.
1 minus 65.5. Yeah.
There we go. Thank you. I went with what you guys gave me. Right. So this is, so this is 1 minus this, right? So what is that?
65.54. Yeah.
So let's say 65%. So there's a 65% chance that if I randomly select a person from Delhi, that person will make more money than a person from Bombay. Yeah. Is everybody okay with that?
Yeah.
Okay.
Yes. Okay. Yeah, it's clear.
Sir, why we did 1 minus 34.45?
It's a greater than, no, that norm dist gives me
Okay.
less than side. So 1 minus, yeah. Sandeep, you had something?
No, same thing.
Okay, that's right. Yeah. Now, does that answer the question?
Another thing, like either we subtract or either we add the distribution, the resulting distribution is always flatter. Because spread increases.
Because variance will anyways increase, added now. That's
But I'm
Variance
also dividing by sample size by N1 and N2.
If N1 and N2 are same, then variance will
Yeah.
increase.
Need not
Even
to
you
be.
subtract or add.
For one, yes.
For one, yeah.
For one, yes.
It will
Not for
flatten.
N, not for N1 greater than 1. Yeah. Surya, you had something?
Yeah, sir. So instead of like 1 minus this formula, even at the last, instead of true, if we give false, that will also come now.
No, it will not.
That's cumulative.
That
That's
false will
cumulative.
give you the height of the curve. It will not give you area under the curve.
Whole height,
No,
yeah, it will not give you.
it will
Yeah.
not. Okay. Sorry, Vishika, does that answer the question that you were asking earlier?
Yes, sir, it is much more clear. Thank you.
Okay. Okay. Right.
Sir,
So,
in which case we add these two, x1 plus x2? In which scenario?
well, I may want to find the additive, no?
Like I'm not able to find or guess any sample, like which in which condition x1 plus x2. So
So, take the same example, no?
yeah.
So let's say I take a random person from Delhi and a random person from Bombay. What is the likelihood that their combined salary will be more than 100 lakhs?
Okay, got it.
Does that make sense, guys?
Yeah, it's
Their mean was 40 and 38. I'm saying if I randomly select a person from Delhi and a randomly select a person from Bombay, what is the probability that they will combine? A Mumbaiite is marrying a Delhiite. What is the probability that their combined household income will be more than 1 crore?
Yeah.
Got it. Thank you, sir.
Yeah, fine. Okay, folks, I think we are at break time. Can we take a break and come back and do that Columbia example before I move on to the next one?
Yeah.
Yeah. Sorry, say that again. No. Hold on. Ashutosh, hold on. What is 3 times now? Yes. No. Where am I claiming that?
Comparing Bombay and Delhi, right, for now.
Okay, not from our example. No, sorry, Ashutosh, I don't understand the question. So, you have to tell me what are the original distributions of Delhi and Bangalore. Okay, so if I have these distributions between Delhi and correct? Yes. Okay. You're sure. What you're asking is the following, no? Okay, perfect. Yeah, go on. Exactly. That is correct. You are basically asking what if I select one random person from Delhi, what is the probability that their salary will be more than 3 times that of some random person that I select from Bangalore, right? Or Bombay or whatever. Is this basically what you want? Yeah, absolutely. So then you are basically asking the question, the probability that x1 minus 3x2 is more than 0. What is this? This guy will have what? A mean of mu1 minus
3 times mu2.
3 times mu2 and sigma 1 squared. Can't forget that value of 3.
3 square.
Absolutely right. Remember we have that in the slides. Don't forget. What is this? A1x1 plus A2x2 is what? A1 times mu1 plus
A2
A2 times mu2. And then your standard deviations or whatever, the variances get multiplied by A1 squared plus A2 squared. Correct? So now I'm going to be dealing with a distribution which is which has a mean like this and a variance like this. Ashutosh, does it answer the question? Okay, perfect. Yeah. Okay.
I
All right.
think
First.
understanding the question and then putting this probability x1 minus 3x2, if we can get that concept well, I think anything we can go with the formulas this way.
Yeah, so the idea is first identify what is the random variable.
Yeah.
What is random in this thing? What is the distribution for? The distribution is for salary, right?
Salary, yeah.
So in this case, what I'm asking you is like represent a variable x1 which represents salary of people in Delhi. x2 represents salary of people in Bombay. And then ask yourself the question, what am I asking? I'm asking probability that x1 is more than x2. Okay. The question that I want to ask you when we come back after, let's say, 10 minutes is, if I draw 10 random people from Delhi and 15 random people from Bombay, what is the probability that the average salary of Delhi will be more than the average salary of Bombay?
So it will be mean of the 10 samples from Delhi and mean of 15 samples from Bombay.
Exactly. I'm taking 10 people from Delhi, I'm computing their average salary. I'm taking 15 people from Bombay and calculating their average salary. And I'm asking the question, what is the likelihood that the average Delhi salary is going to be more than the average Bombay salary? It's a different question than asking one person from Delhi and one person from Bombay. This is the average of 10 versus the average of 15. Okay, everybody okay with that?
Yeah.
Cool. All right. So can we take a quick break? Come back at about maybe 3:50, maybe 10-minute break, 3:50, 3:55, and then we'll start again.
Yes.
Yeah. Okay. All right.
Recording stopped.